Now I'm going to talk about an interaction between a binary variable and a continuous numeric variable, the interaction between transport and mass predicting price, and I'm using this portion of the regression interactions.r code file. So let's fit this linear model. Price is the response variable, and I have transport asterisk mass to indicate that I want an interaction between transport and mass. Transport is a factor, just like before. Mass now is a regular old numeric variable. It's mass in kilograms. The values represent actual numbers. And here is the regression table. The intercept, 86.22, represents the fitted value of price for robots with wheels at 0 mass. So it's not especially useful because none of our robots have close to 0 mass. But it's a starting point for the rest of the terms in the model. The interaction between transport and mass is statistically significant. Its p-value is 0.003. And that means that the relationship between mass and price depends on whether the robot has legs or wheels, or the difference between the robot having legs and wheels in terms of its price depends on how heavy that robot is. We might expect, for example, that it's more important for heavier robots to have wheels, or something like that. So let's imagine that we wanted to estimate the linear association between mass and price in the robots with wheels and the robots with legs separately. What we have here, 1.75, is the slope between mass and price for the robots with wheels, because wheels is the reference category for the transport variable. The robots that have wheels have a value of 0 for this indicator variable, and 0 for the interaction term, because anything times 0 is 0. And so the term for mass becomes interpretable specifically at that point where the robots have wheels. And that means that 1 extra kilogram of mass tends to cost about $1.75 more for those robots that have wheels. To focus on the interpretation here, I might imagine specifying the reference category of transport on purpose in order to interpret that slope for mass. Here, I've specified the reference category to be legs and then refit the model. So now transport is a factor just like it was before, but its reference category is legs, which means the contrast transport wheels will be included automatically, which has wheels as 1 and legs as 0. And the slope of mass is different than it was before. Now it's negative 0.88 and not statistically significant, which means that for the robots that have legs, there's not a statistically significant relationship between mass and price. The robots that are heavier have slightly less price, but it's not a strong enough relationship that we can claim that it would be unlikely to arise due to chance alone in a world where mass and price were unassociated systematically. In the code file, you'll see that I explicitly changed the reference category to wheels and then rerun the model again. But of course, this just gives us the same information that we already interpreted a second ago when we ran the model in the first place, because wheels was the reference category at that point. Here I'm showing them both on the screen so you can see that the slope of mass for the robots with wheels was positive and statistically significant, heavier robots more expensive. The slope of mass for the robots with legs was slightly negative, but not statistically significant. Heavier robots did not cost systematically more or less, or at least we can't claim to have strong evidence that heavier robots costed systematically more or less when those robots had legs. The interaction term is the same. The sign has flipped because we reversed the direction of one of the variables, but it's conceptually saying the same thing. And the hypothesis test of the interaction will never depend on how the lower order terms are coded. As a parenthetical note, it's worth pointing out that the conditional slopes that we just talked about for mass are the same as the ordinary least squares slopes for mass and price in each of those groups separately if we were to fit the model on a subset of the data. So for example, here I've called the LM function with just price as the response variable and mass as the predictor. The data is coming from the robot's data frame. But this time I'm using a subset of the data, all those cases where the robots have legs, and none of the other cases where the robots don't have legs. So this model has 242 degrees of freedom because we're not using the whole sample of 500 robots. Instead, we're just using those ones with legs. And we're doing simple linear regression using mass to predict price. And the slope is negative 0.88. And when I do the same thing, but with the robots with wheels, the slope is positive 1.75. those slopes match what we got when we fit the model that had the interaction on the full data set and looked at the lower order terms corresponding to mass. The hypothesis tests will not be exactly the same because they're based on a different sample size. So I would recommend doing it the interaction way rather than the subsetting way most of the time. And here's an illustration of what those ordinary least squares slopes look like. The top is a scatter plot of price and mass in the case where the transport is legs. So the legged robots are plotted on the top and the wheeled robots are plotted on the bottom, and I fit the regression lines. And these regression lines, like this top regression line, is the ordinary least squares regression line through this set of points for those robots that have legs. And this bottom scatter plot is a set of points for the robots with wheels, and this regression line is the ordinary least squares regression line for that set of points. But these also are the regression lines that you would get from the full regression model with the interaction, focusing on the simple association in the case where the robots have legs, and the other simple association in the case where the robots have wheels.